Right now, as you're watching this, your brain is having a conversation with itself. Actually, billions of them. But what are they actually saying? For the longest time, neuroscientists could see which parts of the brain were lighting up, but they couldn't really hear the conversation. Today, we're going to pull up a chair and eavesdrop on that neural chat using an amazing tool called dynamic causal modeling.
So, this is the big question, right? It's one thing to see that a couple of brain regions are active, but it's a completely different challenge to figure out the flow of information. Who's sending the message, who's receiving it, and who's actually influencing who. It's this incredibly complex network, and to map it out, you need a very special kind of approach. And this really gets to the heart of the problem. Standard brain scans, like an fMRI, are fantastic. They show us where the action is happening, but that's just correlation. It's kind of like seeing that a building is full of people. You know there's a party going on, but you have no idea who's talking to whom, what they're saying, or who's really running the show. To truly understand what's going on, you've got to get inside and listen.
Okay, so here's our game plan for this explainer. We're going to start with the mystery itself, how the brain communicates. Then I'll introduce you to our special tool, DCM. We'll walk through the 5 key steps of using it, see how it adapts to different kinds of clues, learn how it picks the best explanation, and finally, we'll wrap up by looking at what this tool is really good for.
Every great detective has their go-to gadget. For neuroscientists trying to decode the brain's wiring, that gadget is dynamic causal modeling, or DCM for short. You shouldn't think of it like a magnifying glass, which just shows you what's there. No, think of it more like a super sophisticated wiretap, one that lets us listen in on the secret, directional conversations happening between different parts of the brain.
So what is it really? Well, in simple terms, DCM is a framework that lets scientists propose and then test different theories about how brain regions talk to each other. And that term you see there, effective connectivity, that is absolutely key. We're not just talking about the physical wires. We're talking about the actual influence that one group of neurons has over another while you're doing something. This right here, this is the big shift in thinking. We're moving away from the simple question of what parts are on to a much deeper, more interesting question. How are those parts actually influencing one another? It's the leap from just having a map of cities to understanding the highways, the traffic flow, and even the direction of the traffic between them. This is how we get from a static picture to a dynamic working model of the brain.
So you have this incredibly powerful tool. How do you actually use it? Well, it's not just guesswork. It's a very structured process, a clear, logical path that takes a scientist from a simple question all the way to a solid answer.
Basically, every DCM study follows these 5 steps. You start with a hypothesis, a specific question. Then you collect your brain data and, clean it up. Now, step 3 is where the magic happens. You build your models. Each model is a different theory, a different possible wiring diagram for how the brain is solving a problem. Then you test how well each of those models fits your actual data. And in the final step, you compare them to see which one gets the trophy for the best explanation.
But what good is a tool if it can only look at one kind of evidence? I mean, a real detective has to be versatile, and that's one of the coolest things about DCM. It's incredibly adaptable. It can analyze signals from all sorts of different neuroimaging techniques, which capture brain activity in very different ways.
This flexibility is a huge deal. It doesn't matter if a scientist is looking at these slow, methodical changes in blood flow from an fMRI, kind of the tortoise in our story, or the lightning-fast electrical spikes from an EEG, definitely the hair. The core idea of DCM still works. You just use a different mathematical engine that's tailored to the speed and detail of that particular signal. Let's break that down. With fMRI, which has that slower signal, DCM is perfect for modeling the big-picture influences, the major highways between regions. But with the incredible split-second timing you get from EEG or MEG, scientists can zoom way in. They can use much more detailed models of the actual neural circuits to see how specific groups of cells are interacting, almost in real time.
Okay, so this is where it all comes together. The investigation has happened, the evidence is in, and all the different theories are on the table. Now it's time for the verdict. How do we actually decide which theory wins?
And this is one of the biggest challenges in all of science. When you have 2 or 3 or more plausible ideas that could all explain what you're seeing, how do you choose? You can't just go with your gut. You need an objective, impartial judge to weigh the evidence.
And that's where something called Bayesian model comparison comes in. Don't worry about the fancy name. It's basically the statistical judge at the heart of DCM. Think of it like this. It looks at each of your models, each of your theories, and it asks one simple question. How well did you predict the brain data that we actually recorded? The model that provides the most accurate and elegant explanation, the one that fits best without being overly complicated, that's the winner.
Let's make this super concrete. Imagine we're studying attention. Our first hypothesis, our first model, could be really simple. When you pay attention to something you're seeing, it just directly turns up the activity in your visual cortex. A nice, straightforward idea.
But maybe it's more complicated. So our second hypothesis could be that attention doesn't boost the visual cortex directly. Instead, it works by having a control center in the front of the brain strengthen the connection to the visual cortex. It's like a manager telling another department to work harder. It's a totally different circuit, a totally different story.
So we run both models. We let our Bayesian judge weigh the evidence from our brain scans, and bam! It turns out hypothesis 2 is a much better fit for the data we actually saw. And this is the magic of it. We haven't just guessed. We've used real data and a principled method to show that one theory about how the brain works is more likely to be true than another.
Okay, so DCM is clearly a powerhouse, but like any highly specialized instrument, it's designed for a very specific job. And to be a good scientist, or a good detective, you have to know not just what your tools can do, but also what they can't do.
This quote really nails it. DCM is what we call a hypothesis-driven approach. That means it is not for fishing expeditions. You can't just toss a huge pile of data at it and ask, so what's going on in there? You have to come to the table with a specific question, a specific theory you want to test. It's for confirming ideas, not for discovering them from scratch.
And that leads to a few key limitations you just have to know about. First, you have to tell it where to look. You have to pick the brain regions you're interested in ahead of time. Second, it's at its best when you're comparing a handful of clear, competing ideas, not dozens of them all at once. And finally, there's a technical reason, a mathematical shortcut it uses that works great most of the time, but can be a little less accurate if your models get super, super complex. The takeaway? It's a scalpel, not a Swiss Army knife.
But at the end of the day, by allowing us to finally listen in on these hidden neural conversations, DCM is changing the entire game. It's moving us closer than ever to understanding the precise circuits that create our thoughts, our memories, and maybe even our consciousness. And that leaves us with the most exciting question of all. Now that we can finally hear the brain talking to itself, what secrets is it going to tell us next?